In this problem we have a sorted array, but that array is clipped from the middle. So a sorted array, and this array can contain duplicates. So we can have equal values like this. So this is a sorted array. It can have duplicates. These flat lines denote duplicates. So we clip it and put this half before the other half. So it's like this. And then this smaller part. So it can go up till here, so that if we append it here, it remains sorted. So it can be equal. So this is different from version 1 of the problem where there were no duplicates. So it was a straight line. In this case, we can have duplicates. So these flat lines are there, and that complicates the problem. So how can we sort it? So first, let's see a complicated case where we have something like this. This is possible. And then we have from here onwards we have this flat line. So this is same as this. These all values are same. Let's say these denote 3. So these may be 4, 5, 6, 6, again 3, 3, 3, 3. So let's say we are searching for 5. So we come to middle. Let's say middle is here. So there is one special case. This case I am drawing is a special case, and it's the tricky case that increases the time complexity of our solution. If this case is not there, if it's a increasing array, then we can do it in logarithmic time. But for some cases, we cannot do anything. For example, let's say this scenario. So middle is here. We see that left value is 3, middle is 3, right value is 3. We don't know which part to search, whether to search in the left part or right part. So in this case, middle is less than the target that we are searching, but if this tail is longer, you get the idea. And we have like this. Again we are searching for 5. Again this is 3, but this time mid is here. Mid is 3, left is 3, right is 3. So we have no clue which part to search. In that case, we cannot do anything. We have to just increment the left and decrement the right by one step. In all the other cases, we will eliminate half of the parts. So on average, we will do it in logarithmic time only, but for some iterations, so a binary search converges in log n time. If the size is n, first time we reduce it to half, next time we reduce it to 1/4, then 1/8, and so on. And in log n time, we complete the search. So most of those steps will be this only. But in some of those intermediate steps, we will encounter a situation like this, where mid is same as left is same as right, and we cannot do anything other than incrementing left and decrementing right. Let's take another case where it's not the case, where let's say middle is here. The same example, but middle is here this time. And let's say this value is 7. So middle is more than 5. Let's forget that. So in this case, left is 3, middle is 7, right is 3. So middle is not same as left and right. So we compare it with left. So we see that left is less than middle. So we know that this part is sorted. Now we will check whether our target lies in this range or not. That's very easy. Compare with left and current value. So 5 lies in this range, and we know that this part is sorted. So we know that we can get rid of the right part completely. So now we have a sorted array, and we have to search for 5 in this range. So log n time from here onwards. The other case is that this part is not sorted. That is, left was not less than mid, but left was more than mid. So let's take an example. And let's say we have this one. Mid is here. So left is more than mid. So this part is not sorted. In that case, this part will be sorted. So again, compare whether the target lies in this range or not. If it lies, we will search only in this part. If it doesn't lies, then we can get rid of this part. So in both the scenarios, we can either select that half or reject that half. So we will be reducing the problem by half. So this is the only minor difference from a normal first version of this problem, rotated sorted array, problem 1, where duplicates are not allowed. So this tricky case where we cannot do anything. So let's write the code for this. But on average scenario, if we have log n steps to converge, it may take maybe log n plus 5 or log n plus 4, some constant value on average case. But you cannot justify that. So worst case we will assume O of n. But on average it will be O of log n. So let's write the code for this. First we will write in C++, then Java and Python. So L and R denote left and right indices within which we will be searching. So if nums mid is same as target, then we are done. This is the best case when we found the match. Else we continue the search. So what we will do, we will check if nums L is equal to nums mid and nums R is equal to nums mid. So this is the tricky case that we saw here, the only case which is different from the first version. Then we cannot do anything. We don't know which part to search. So what we will do, we will simply do L plus plus R minus minus. Else if nums L is less than equal to mid, then the left part is sorted. So either we will pick that left part or reject that part depending on whether target lies there or not. So if nums L is less than equal to target and nums mid is more than target, then target lies in left part and left part is sorted. So what we will do, R equal to mid minus 1 because mid is more. Else L equal to mid plus 1. In this case we ignored the left part. In this case we picked the left part, and this was the case when left part was sorted. The other case is right part is sorted. We will either have left or right part sorted. We cannot have both parts unsorted because we have a monotonic increasing line. Somewhat at some places it's equal also, but if we break it and swap these two parts, middle will be either in this part or this part. So depending on that, either left part will be sorted or right part will be sorted. Both parts cannot be unsorted. So the else case is when right part is sorted. So again check whether the target lies in the right part or not. Depending on that, we will either pick or reject that. Very simple. So nums mid is less than target and nums R is more than equal to target. Then L equal to mid plus 1, else r equal to mid minus 1. Exactly similar logic, both these cases. And finally, we will return false. If it doesn't encounter this situation for any value and left and right have become now equal, or left is more, then we did not find it. So let's see. So one bracket is extra, two this closes here, open, close, okay. And our answer is wrong. So let's see why it is wrong. So left is 0, right is nums.size minus 1, mid is fine. So it should be nums mid, so don't make these mistakes. Mid is also integer, nums mid is also integer, so there will not be any compilation issue. I hope I have not made the same mistake anywhere else. And now the solution is accepted. And it takes 8 milliseconds, so we are right at the peak of distribution, somewhat better side. We are roughly better than 87% of the submissions. Now we will do the same thing in Java and Python. So that is the only case which is different, this one which I am emphasizing. Java solution is also accepted, and here we take 0 millisecond. Finally we will do it in Python 3. and the Python solution is also accepted.